This is a house. Could be my house or your house or just any house. And there are for sure people living in it. Which means they also want to heat the house in the winter. They are cooking. And they're taking showers. All those things increase the temperature in the house, the moisture level, and also the pressure. This pressure difference makes the moist, warm air from inside the building wanting to travel outside, right through the walls. And since no one ever believes that air is really traveling through walls, and to answer our question if walls are really breathing, I did build this highly efficient but not so scientific thing, which is replacing that drawing of the house now. To demonstrate the pressure differences between inside the building and outside, I built that boxy looking lid for it with a hole in it to be able to attach my shop vac to it. That setup is creating a way bigger pressure difference than it would be between inside and outside a building. But in the end, it's just speeding up that whole process. Walls have weeks and months and years for. An alignment laser and some burning wood chips make the air inside the building visible. MDF, drywall and OSB are the three materials we are going to suck some air through. But before that, let's test the whole system without the resistance of any of those materials in. Ready for it? This is gonna be quick. I'd say it took around 2.5 seconds to suck all that smoke out of the box. Let's now suck through some material. The first one is gonna be MDF. We can right away see something happening. Because we do really suck air through that MDF board. Fresh air is coming through that opening in the back of the box. And all that smoke is moving more towards the top of the box. And after around 2 minutes, that whole box was smoke free. I knew this is going to be quick with MDF, but I didn't expect it to be that fast. The next material on our list is drywall, which is a wheel building material, and I'm already curious to find out how long it's gonna take with this one. To my big surprise, something happened right away. And I thought this is gonna go as quick as with the MDF. But then it quickly turned out that this is gonna take way longer. After around 11 minutes, almost all of that smoke was gone and I decided to relieve my shop vac from all that stress. The third material we are trying to suck through is OSB, and this time I turned the lights down. There is obviously something happening in there. Way slower than with the ones before, but something's going on. You can see this better if we compare minute 1 to minute 14, where I had to stop the test because I was afraid of my vacuum dying. You can't see the back of the box on the left side, which you can on the right. So there is obviously some air exchange going on. It's just way slower than with the ones before. The next material we are testing is a vapor retarder. A vapor retarder is a special membrane which is used in buildings to allow some air to travel through. To be able to do that, I had to put the retarder in front of the MDF board. And we should actually see pretty much the same results as with the OSB. And the only difference I did see compared to the OSB was that my laser battery died. Sorry for that. I guess we can now already give an answer to the question of the title of this video, which was, do walls actually breathe? And we can answer this with yes, walls can breathe. But there's still more to that, because it's not always like that. We did test two materials which didn't really stop the air from traveling through them. And we did test two other materials which made it way harder for the air to travel through them. Materials like OSB and that membrane are called vapor retarders. There's a third category of materials which don't let any air through, and those are called vapor barriers. But a vapor barrier is not always the right choice. You can compare it to one of those old yellow rain jackets, which keep you dry from the outside. But once you start producing some kind of humidity, you will faster get wet from the inside than from the outside, which is not good for your climate. You can compare a vapor retarder to one of those rain jackets you wear nowadays. They also do their purpose from keeping you dry from the outside, but also allow your humidity to breathe through the jacket, like a retarder would do that for your building. And that's definitely a big advantage for the climate in your house. That was one of many reasons why I chose OSB as vapor retarder for my shop ceiling. If you'd like to find out more about this, just watch that video after this video. I'm not the first guy that found out about all this, and Wikipedia Germany, for example, is full of informations. That resistance of materials letting air and moisture through is called Wasserdampfdiffusionswiderstand in German. That would translate into something like water vapor diffusion resistance. It's basically just a number that tells how high the resistance of a material is compared to air. So air would have 1, the drywall we tested would have 10. OSB has a pretty wide range from 50 to 300, which again comes from the fact that there are different kinds of OSB with different glues and different amounts of glue in them. The one we had should rank around 150. Down here are all those polys with a very high resistance rate. Polyethylene, for example, is what a normal vapor barrier is made of. So it is common sense that different materials have different vapor resistance levels. You can nowadays say that vapor barriers are not good for your building, and they are often responsible for a high moisture level and mold. A modern wall is responsible for a good climate in your building, and it should be able to breathe to prevent from mold and all that. But this breathing of your walls brings another risk with it you should be aware of. This right here is a model of that ceiling I did build over my shop, and there's actually a lot of building physics behind all that. Warm air can contain more vapor than cold air, and the air is getting colder and colder while it is traveling through that structure. And it should never get that cold inside the structure that it's not able to contain all that vapor anymore, because it would then get oversaturated and you would have water in your structure. And that ruins everything. There are very cool tools online which help you avoiding those mistakes, like that U-value calculator from Ubicus. That's actually a German homepage, but you can set different languages and you can very simply click together any kind of construction, like our ceiling model. You can just click through from top to bottom and choose for your different materials, insulation and whatever, and get a ton of information then. We have 2 layers of drywall, so let's put them in. So, and as you can already see, we would have a water problem in here. So let's add that OSB board. Still not good because the outside of the OSB is too cold, so let's add insulation to change that. This already changes things, and we can in that insulation layer also add the timber beams, but all that needs to be 200 millimeters. Does already pretty much look like our model. The only thing missing is that membrane on the outside now. And we are done. I mean, how cool is that? That takes just a couple of seconds and we do now get a ton of information. We can, for example, check the U-value of the whole construction. For my US friends, the U-value is the inverse of the R-value. In Europe, we are always dealing with the U-value. And we can for sure check the moisture level in the construction. I don't want to go into details again, but that black line should never be touching that blue line. And as we can see, we are good now, but we could also go back to the settings and simply take out that OSB board and check what happens then. And we would, how expected, have a water problem. In my eyes, this is a really helpful tool if you're interested in things like that, and it's definitely worth spending some time checking out different settings and stuff, and you can learn a lot from that.